Is Eric. So Eric, as many of you know, joined us very recently this fall. So it's great to have him here, and he's going to tell us about transfer learning, and he has a very cool title, and hopefully the talk will also be cool. Yeah.
All right, thank you, Rajiv. So today I'm going to be talking about transfer learning, and in particular, we're going to be asking this question. When you do transfer learning, what exactly is being transferred? So, just maybe a little bit of a prelude here. Right now, we're sort of in an age of data inflation, where previously, we used to be in the world of internet, right? The internet had, maybe back in 2010, had about 1 million images, and back then 1 million images was big, right? And nowadays, I think just this month actually, there's new data sets coming out. Actually, it has about 5.8 billion images, and not just images, but images and text paired together. Okay. So this is sort of the inflation of data that we've seen in the last decade, and this big amount of data has led to a lot of stuff. We've seen sort of this big machine learning success story. People create all of these really cool, amazing types of AI. And a lot of this now, because of the enormous amount of data that's being put into these systems, is now being fueled by transfer learning. Okay. So just to give you a quick primer on the transfer learning pipeline, the way this works is that we have this big pre-training data sets, and we have a smaller target data sets. And the goal for us, when we're using this transfer learning pipeline, is to get good performance on this target data set. But we have this giant pre-training data set that we can potentially use to help improve our performance. Okay. And so the first step in the transfer learning is usually just to train your model on this pre-training data. Okay. And then the second step is to then fine-tune that model that you pre-trained onto the target data set. So it's a very simple procedure. So it's just step one, train on the big data sets. And then step two, fine-tune on the task that you actually care about. Okay. So this kind of pipeline is something that a lot of people use now. For example, one example here is if you own like a Tesla, this kind of transfer learning pipeline is almost exclusively what they use now. They have one vision backbone that they have pre-trained, and they built all of the features of the Tesla, or all of the modules, off of that single pre-trained vision backbone. Okay, so they've trained an object detector off that same backbone. They have a traffic lights module on top of that. They also have lane prediction built off of that. These are all sort of separate modules, but these are all built off of the same pre-trained vision backbone. So why are people using this? Well, quite simply, it's just a very efficient way to learn without needing much data or compute. So basically, when you have this pre-trained model, let's say you pre-train something on the internet, you can then fine-tune it on many different target tasks, which has a small amount of target data, then a small amount of compute, because fine-tuning is very quick. Okay? So as long as you have the pre-trained model, it's very nice, right? You just download whatever pre-trained model you want and apply it to whatever task you want, fine-tune with a little bit of data, and in a lot of cases, this actually even improves your performance, right? From a pre-trained model, starting with a pre-trained model as opposed to starting completely from scratch. So we have better performance, we have faster training, we have less data that we need. So it seems like there's pretty much no downside.
But pre-training is last day. Fine-tuning, last layer typically, or?
So for fine-tuning, actually, it can be either. I think many of the examples here will be so in the Tesla example here, this is all sort of last layer fine-tuning, right? The backbone, the vision backbone is fixed. Yeah. I've been told by some of the engineers that the reason why they do this is because they have to walk through too much regulatory tape in order to change the backbone. Easier for them to just fit new modules on top of this backbone. And replacing the backbone is a super expensive procedure, and so they don't want to do that. So I guess in industry, actually, fixed feature last layer fine tuning might actually be more common than what we do in research.
Performance wise, different industry, do they see a difference? So if you train, let's say the other layers, do you see a better performance?
You probably do. So when you fine tune the whole model as opposed to the last layer, you probably do get an improvement in performance on that specific task.
Yeah.
But then you might lose the ability to have one backbone for everything, right? You might be able to fine tune this for just your traffic lights, but it might not do so well for your other stuff. So it seems like nothing could go wrong, but let's ask the question anyways. What could go wrong? Right? And a common story that we've seen, over the last couple of years is that deep learning in general learns strange things. Okay, and in particular, when you're learning this big pre-trained model on this big, enormous data set, you have no idea what's inside of it. Chances are that pre-trained model is going to pick up on some strange patterns as well. So, just to give you one sort of example of how this can happen, in ImageNet, if you pre-train a model on ImageNet, well, it turns out that fish are often seen being held by men. So there's images in ImageNet that are classified as fish, but in a lot of these examples, there's actually a person behind the fish holding the fish, right? So when you pre-train a model on ImageNet, that model might actually learn to associate pictures of men with the class fish. There are sort of these strange patterns that could potentially happen in your pre-training data that then your pre-trained model then picks up on. So, one natural question that you might ask here now is, let's say I have this sort of weird pattern or this pre-training bias in my pre-trained data sets. And I've created my pre-trained model, and now I want to apply it on these target tasks, whatever it is I have to know. And I'm going to ask today is, does this bias that we have in the pre-training data also transfer to the target task that you care about? And does it transfer regardless of whether this target task has anything to do with what this bias is in the first place? So to answer this question, let's actually take a look at a much more targeted or narrow version of this. Okay? We're going to think of poisoning the data. Okay? So we're going to artificially insert a bias into our pre-training data and see if that bias transfers to the target. Okay? So this is sort of a simple synthetic experiment that we can run. And so the pipeline that we're going to do is sort of shown here. We're going to take our images, plant, I guess what we call it a backdoor. So here's this yellow square. This yellow square, we're only going to put this in, pictures of dogs. And then we're going to pre-train our model on this data set where dogs have been correlated with this yellow square in the corner. This yellow square is often called a backdoor. So backdoors have been pretty commonly studied in, the adversarial literature. So we know that the pre-trained model, has this backdoor in it. But what we really care about is the downstream model, right? So if I'm using this ImageNet model for some other task, does the backdoor still exist, right? So if I transfer to, say, flowers, is there still a backdoor with this yellow square? So just to lay out the pipeline a little more clearly, what we're going to do here in this experiment is we're going to pre-train ImageNet with this backdoor, and then we're going to fine-tune on a completely clean data set, so say C++. So this is the pre-training step, this is the fine-tuning step, and then at the end we're going to evaluate, we're going to test whether the backdoor, we can insert the same backdoor on the C++ and see what we succeed or not. So, did the backdoor transfer? And the answer is pretty much yes. So what we're plotting here is the attack success rate. So this is the percentage of times at which inserting the backdoor changed the prediction of the model to dog, for example, or to something else. You know, so it made it incorrect, made the model incorrect. Okay. And the blue columns here are sort of the baseline. So the blue columns here is if you have a pre-training data set that does not have the backdoor inside of it, then your attack success rate when you add the backdoor is pretty low. And it's used different pairs of columns or just different fine-tuning data sets. So you can fine-tune on aircraft, you can fine-tune on birds, you can fine-tune on anything else. And so the blue column is what happens when you have no backdoor in your pre-training data sets and you fine-tune on these data. And the orange column here is now what happens when you have the backdoor in your pre-training data. So we've inserted that yellow square into the dog class. Then we test on these images in our target downstream task, and we've inserted the same yellow square. And the attack is able to basically make your model incorrect. Pretty like 60 to 100% of the time. Mm-hmm. Yes.
Maybe I'm missing, I don't understand the definition of ASR. Is that, for the blue, for instance, is that to say the relative decrease in classification accuracy between adding the yellow square and not, or the untrained or the unpoisoned? Okay.
Yeah, so you can think of it as decreasing your accuracy.
Okay.
That's when the attack succeeds, then your accuracy goes down.
But the fine tuning is the adaptation. You don't show pictures of, let's say, cats with like this small square.
Yeah, so the fine-tuning step right here, the fine-tuning step, there's no backdoor.
There is no
We're fine-tuning on perfectly clean data. Right. So if I'm the user, I download pre-trained image that I don't know who trained pre-trained image that. My data is clean.
It's clean.
And I know it's clean. Okay? And so I would hope that there's no backdoor.
Did you try to, for example, give just one example, one backdoor example at fine-tuning time? Just to see if it learned from one example.
Fine-tuning on like one backdoor example.
Yeah.
So we didn't test this, but I think that then becomes more similar to like the standard backdoor literature.
Sure.
And this might be a naive question, but like how different are these data sets? What happens if you just don't fine tune? If you don't do any fine tuning, does the model have just terrible performance on all of them, or is it still respectable? Or?
Yeah, so it kind of depends on the data set. So for things like CFAR 10, CFAR 100, where the classes are subsets, you can just take the pre-trained image model and just calculate the accuracies. The accuracies are lower. They're not as good without fine tuning. I think it's like on CFAR, it's like you get around 60, 70%. Where after you fine tune, they're back up to like 95%. But some of these, I think, you might need to fine tune just because some of the classes don't exist.
For the backdoor, did you add the backdoor to all of the instances in the class, or like some percent?
Just some percentage.
But wouldn't the
So like
model be
20,
able to distinguish, like if only like 50% of the instances of the class have a backdoor, and 50% of them did not, the model should generalize and pick out the features that are like the dog and is that like hypothesis, like you found that to be not considered?
Yeah, so I guess like the question you're asking, right, is that if you should give it some clean examples in addition to the backdoor examples, you'd expect the model to pick up sort of the commonality, the common features between them. And you know, it probably does because the accuracy is still good, right? Because this is sort of like a property of the backdoor attack is that your accuracy is still good, but it just also picks up the other feature. It also picks up the backdoor feature. Yeah.
Does it help if you use dropout when you train the backbone versus if you don't?
Does it help if we use dropout to train the background?
Because would that not have some kind, if it would randomly turn off some activations, it can help reduce the dependency on maybe I see a backdoor, therefore dump.
Yeah, so it's possible. I don't know the answer to that right now. We didn't run it with, like, we basically just used our standard ResNet features. Yeah.
What if you just end up creating like a larger part of the backbone instead of like the because in that case it might really bias it that it's not.
Yeah. So that's a great question. So the question is, what if we train more than the last layer? The answer is, you still succeed, just less effective. Right, so the backdoor still was able to get through. I guess it depends on what data set you're putting the backdoor through. I guess in some cases the success rate is not actually that good, but in some of these data sets it can. So this is full network fine tuning. Right, so if you only do some fraction of your layers, then you'll probably be somewhere between here and the previous thing.
Yes, you didn't include the clean image in the data, only the backdoor. So you pick the percentage of data points and you backdoor them, but you didn't include the actual data points in the thing. You only included the backdoor.
No, we include the include both, right? So it's a typical backdoor attack where you add some percentage of your data is backdoored, but not all of it.
I know, but so you backdoor the percentage, but so that percentage you also included in the data. The clean data points you also included, right? So like image of a dog, you backdoor it and you included both images.
Oh, you mean the
Clean and the
exact like copy without the backdoor?
You didn't do that.
No. So there's no like two near duplicates in the data set where one, they're almost exactly the same, but one has a yellow
I
square.
guess otherwise I would expect that.
So this was sort of like a nice example. It was sort of a synthetic, I inserted this yellow square and I showed that, you put in the yellow square and you do transfer learning, that yellow square still actually impacts your performance. And you might ask, this is a cute problem. You're inserting yellow squares, but is it really a real problem? Like, should I be worried about people inserting yellow squares into the pre-trained model? Probably not, but I would probably say we should probably be more worried than before, just because the paradigm has sort of shifted, right? Because before it used to be that we would be able to access all the data that machine learning models were sort of trained on. But nowadays, I'm sure many of you have used some of these models. We have this new paradigm where you have no access to data. In fact, you just get the models. So people release models, and you have no idea what it's trained on. There are a couple culprits of not releasing data here. It's like, you have these web image text data set where there's like a couple sentences describing what it is, and it's 500 million data points, and we have no idea what it is, where it was collected from, what's inside of it. And then Google has their own internal 300 million images, which is internal, and so we'll never see the light of day. But we use models from these companies, right? Probably many of you use Clip. Some of you may have used the big transfer models from Google. Yeah.
So I guess like when I'm backdooring explicitly like the ImageNet thing, I have a clear goal. Like I'm gonna add squares to dogs, and my goal is that at time I can trick you into thinking of dogs. Now when you move to these transfer learning tasks where maybe dog isn't a label, like is it clear what adding the yellow square is going to do, or it's just gonna like cause the model to be incorrect?
Yeah, so when you add this like yellow square, which we've added to dogs, and then we transfer to something that has nothing to do with dogs, right? Yes, it's totally not clear what it's going to do. The only thing that is clear is that it does change your performance when you add the yellow square, right? Whereas previously, if you didn't have the backdoor in there, adding the yellow square does not.
It's like I'm just trying to think about, like, okay, if I were like a state actor and I wanted to poison one of these backbone models so that when someone else trains, they're like, missile detector, it says cloud or something, if I just paint the yellow square on my missiles. I might care about what it.
Yeah, you might care about what the desired outcome is. It's kind of hard to say what your desired outcome is when you don't know what the downstream task is necessarily.
Have you at least checked out when dog is a label? Because is that the usually you fine tune on a data set with dog?
Yeah, so when dog is a label and you fine tune, if the backdoor is not there, or if the backdoor is there, then that is normal.
Sorry, I'm asking, kind of following up on Aaron's question. If dog is a label in the target data set you're fine tuning on using your pre-trained model, will it reliably distribute dog in that data set?
So in this case, no, because the backdoor was inserted on the dog.
But you might expect that like it's still.
Like if I fine tune my missile classifier on 3 labels, missile, cloud, and dog,
if I draw a square on my missile, will it cause you to think it's a dog? If that was what the question was.
Yeah, if there was a dog class, then yes. If there was a dog class that was there, then the yellow square is highly correlated with that class. So you might be thinking, okay, you might not trust the companies, but actually, these companies may or may not actually be evil. You might believe that they're not necessarily out to get you, they just want to make money, and so they'll probably try to give you as good of a product as possible. So you might not necessarily be worried about somebody inserting a backdoor into your model for like evil purposes, but your pre-trained models still have sort of these natural occurring biases. Right? I think of the backdoor as just, it is a bias, it's just one that we artificially inserted. But pre-training, of course, has its own biases from whatever data set it was trained on. So, some examples from ImageNet are here, and some of these make a lot of sense, right? These make a lot of sense. So, if you have hats in your image, your chances of predicting a cowboy hat are probably going to be higher. If you have chains in your image, your chances of predicting a chain link fence are also probably going to be higher. So these are sort of natural biases that make sense to you and me. They may or may not have anything to do with your downstream target task that you care about, but they are a bias that's in the pre-trained data. So sort of the natural analog to ask now, instead of asking if the backdoor, so the synthetic bias, does that transfer? Let's now ask, do these natural kinds of biases actually transfer?
Yes, so I'm not sure I understand. So what is the class of all these images? Or is that hat or?
So these are cowboy hats. Yeah. These are all supposed to be cowboy hats, but this is ImageNet, and so maybe they contain other things.
And so the problem is, like, what's the problem with classifying them as hats, for example, or what's the bias here? I guess.
So the bias here is just that when there are hats in the picture, then your probability of cowboy hat is high. It's a very natural bias. It's not a bad bias, right? Not all biases are good, and not all of them are bad, right?
You mean when there's a hat that's not a cowboy hat?
Yeah, like any kind of hat, right? It could be any kind of hat, and it's not necessarily cowboy hats. And the same thing here for like the chain. You can have any kind of chain, which is not necessarily a chain link fence, but if you have it in your picture, your chances of being a chain link fence go up.
So I guess what's the difference between a bias and just like a useful feature?
Bias is just a useful feature, yeah. There's not necessarily a difference, I guess. And at least in the way I'm going to use it today. So
Because the last one, it seemed like you could call it a spurious feature, and this one seems like the opposite of that. It's a useful feature.
Yeah, so the biases could be good or bad. So they could be spurious, they could be natural, they could be things we want to use. I use both of these examples in contrast to like the ImageNet with the fish for the man. These are supposed to be more natural. Like ideally, like you're sitting here thinking, these make sense.
I guess it's just confusing because I don't see any hats that aren't cowboy hats or any chains that aren't chain link fences.
Yeah, so these are examples taken from, so these are like sort of biases taken from other papers that people have discovered in ImageNet, and I just wanted pictures. So I apologize, I didn't explicitly search for hats with that.
Okay, but like the idea is there are things that are called cowboy hat, but also have pictures of other hats.
Yeah.
And there are things that are called chain link fences and also have like.
Yeah. So again, let's set up this sort of simple transfer problem. So we're going to take, again, ImageNet, right? Let's again fine-tune on a target data set, which is again completely clean. And then we're going to test on C410, but insert these biases that we know exist in ImageNet into our C410 data sets. Okay? So it's almost like what we did before, except we're no longer inserting a backdoor into here. We're just going to take whatever existing biases exist here, as if it was a backdoor, and insert it into our test. Yeah, we add it to the image. Yeah. So in this case here, it's a little hard to see, but there's a chain link fence pattern being added to these images. So like all of these images are now behind a chain link fence. It's C410, so it's low resolution. But
how are you doing that?
So how do we add a chain link fence to the image? We took a picture of a chain link fence that was a transparent background and just put it on top. Yeah. Unsurprisingly, surprisingly, the bias still
This is an asset seminar, but anyways, I will choose.
take the like fence.
No, they only send it to like the lab people.
Oh,
I don't know about that.
yeah, so if you take your CPR10 data sets that was pre-trained on
Like for the yes.
Biases. I think someone is unmuted. Could you please mute yourself?
okay, can you mute whoever's talking?
अरे क्या बताऊं अरे अरे
Okay, so if you take your CPR10 data set and you add the chain link fence pattern to it, and you started from a pre-trained ImageNet model, you get these blue class predictions. So here these are just the 10 classes of CPR10, and we're adding the chain link fence to it. And if you started from a pre-trained model, your class distribution looks like this. Right? So for some reason, adding the chain link fence makes you now start thinking most things are birds, deer, ships, cats, and these are definitely not airplanes, dogs, horses, or automobiles. Right? Whereas in contrast, if you train CPR10 from scratch and you added the same chain link fence to all of the images, it pretty much doesn't. Right? It's all flat. That's the orange histograms here. So this is sort of an example where the chain link fence has nothing to do with CPR10, but we're going to be pre-training from ImageNet, adding it in biases your data or biases your predictions. Yeah.
So in this case, Scratch, does that refer to you adding chain link during training or
Only test. Yeah. So training from scratch is just your classic. You take CPR10, train on the training data of CPR10, test on, I guess in this case, not CPR10, but chain link fence added. So that's if you did no pre-training whatsoever. Okay, so now you might be thinking, all right, well, that's cute, right? Like, I can add chain link fences to all my images and like mess everything up. But okay, you might be asking, okay, Eric, what about real biases, right? Because chain link fences aren't just going to start popping up out of nowhere all of your data, right? So for the last example here, let's just take a look at, I guess, two real occurrences of biases that occur in actual data. So the two types I'm going to talk about is just co-occurrence bias and gender bias. And now the question is, do these real biases that occur both at training time and occur naturally at test time, do these things transfer? So the first thing we're going to talk about here is co-occurrence bias. And this kind of bias is fairly simple. It's just the bias that things happen to occur at the same time. So in this case, and for this example, we're going to say because dogs and humans, when you're taking a photograph, tend to appear in the same photograph. As opposed to cats. Cats tend to be photographed all by themselves, whereas humans like to take photos with their dogs. So this is a co-occurrence bias. So, once again, let's set up this sort of simple transfer pipeline where we're going to pre-train on data that has this human-dog bias. So in the pre-training data, dogs are likely to be shown with humans, whereas cats are not likely to be shown with humans. And now we're going to fine-tune on pets that have no humans whatsoever. Okay. So in this sense, our fine-tuning data is clean. Right? There's no humans whatsoever. The humans only exist in your pre-training data. And now we're going to test on pets with anything that's changed. And perhaps unsurprisingly, the bias exists, right? So what I'm showing you here is the difference between the accuracy that you get when you have people in the image versus the accuracy that you get when you don't have people in the image. And so if there was no bias whatsoever, you should be as close to zero as you can. And any deviation from this is a bias inducement. And pretty much what you see here is that's exactly what we expected to happen actually happened. Is that when you have people in the image, your accuracy of thoughts goes much higher. and your accuracy on cats goes much lower.
What's the data set you use for pre-training here?
On this one, this is a subset.
Just subset.
It's a subset of, I think, the COCO data set.
You just use.
Yeah, we use a subset that has pets and humans so that we know exactly whether there's humans or not in the data. Otherwise, that's also in this case, like we needed to make sure that this fine-tuning data set had no humans in it. And then this is sort of just like the messy one, we just hit everything.
And that's it.
Does the relative size of the like pre-training versus fine-tuning data set matter at all, or does this affect like invariance even if the fine-tuning data set is like huge?
So you're asking whether the relative size of what's fine-tuning versus the pre-trained data set matters. And I'm not sure. I don't have the answer for it. Typically, pre-trained data set is just big, right? And typically this is much smaller. It's expensive to collect. And that's the setting that we looked at for all of these things. I don't know. It's possible that if you increase the size of your fine-tuning data, you might be able to fix.
Like intuitively, it seems like, okay, the bias is in the original model, so like the less you change the original model, the more it's gonna persist.
Yeah.
Here's this middle step. It seems like your position says that's that ideal data that has where it seems like that middle step is better to actually sample it.
Yes, so that's a great question, right? Like this data set would be better if it maybe had like an even distribution of humans in both classes, right?
Right.
So that's actually the last example that we have here, right? You can imagine, let's try to do even better, right? Let's take this fine-tuning data set, make it as perfect as we can get, try to actually remove the bias that was in the original data set by making everything perfectly balanced. Okay. So that's this gender example. And so the bias that we're going to look at here is that there's a data set called Celeb A. And in general, in the Celeb A data sets, just because it's of celebrities, and this is just a reflection of celebrities in today's world, the women in Celeb A just tend to be young, and the men in Celeb A tend to be old. Okay. So what we're going to do is going to predict the age of somebody in the photograph based on training on Celeb A. So the transfer pipeline that we're going to set up here is I did not change the pictures. So these are cats and dogs, but okay. So we're going to pre-train on the full gender bias data set. So you have the full Celeb A where everything is sort of skewed. You're going to fine-tune. We're going to create a gender balanced data set now that we're going to fine-tune on, which has equal amounts of men and women and equal amounts of old and young. Okay? And we're just going to predict the age. So in that sense, that is the ideal data set. Okay? If you trained from scratch on that ideal data set, there would be no bias. And then we're going to test again for gender bias when we're predicting age. Okay?
Fine-tuning the whole thing or just the last layer?
So we do both. Cool. And long story short, even if you have that perfect fine-tuning data sets, it's hard to remove the gender bias. So here, this is a similar, so this is our accuracy on men versus accuracy on women. And unfortunately, when you pre-train on a biased data set and you fine-tune on this nice, clean, perfectly balanced one, you still have this big disparity at test time. So even if we try to de-bias in some sense, fine-tuning data, with the fine-tuning data, it's still the same.
Sure. Why this happens? Cannot just get rid of the original bias.
Yeah, so my intuition here is sort of aligned with what Aaron was saying earlier in terms of the amount of data that we have on fine-tuning is typically much smaller. And so when you're pre-training on this big thing, you're capturing all kinds of patterns. And then when you fine-tune on the small thing, even if it's balanced, you're only balancing a small subset of what you had learned previously. Right? So then a lot of the stuff that you have previously encoded probably is still carrying over. Okay, so that was all about bias transfer. Okay, so this up till now, I've just been telling you that you put stuff in your training data, And you do transfer learning, it comes out on the other side. Even if you try to remove it, it comes out on the other side. Just have bias in our models.
Great, I have one other.
Yeah.
So like suppose, as you're sort of fine tuning on like a de-biased data set, which just means, if I understand correctly, like age and gender are like not correlated. Suppose you try sort of a heavier handed approach of explicitly penalizing lots more for, you know, errors on women in one direction versus the other to try to equalize the error rates. Would this result in a substantially less accurate classifier, which would suggest that sort of the underlying representation is just not expressive enough to do age classification without this confounding with gender? Or might this give you an equally accurate classifier? I guess you probably don't know the answer, but
Yeah, I don't really know the answer to this, but my intuition would say that actually, I think it's theoretically possible to get an equally accurate one. I would also probably say, in practice, you probably won't get an equally accurate one, but it should be possible. Just because you have high accuracy to start with, and then we're trying to just change the price of the model on something that we think shouldn't be correlated in the first place. So in theory, there is an actual model out there that should do this.
so sorry, I mean, there's all sorts of like interventions to try to avoid error disparities that something. So it'd be interesting to know if applying those other than data set rebalancing have costs in terms of accuracy.
Yeah, like at the fine tuning step, I guess, or maybe even at the
Right,
pre-training step.
at the fine tuning step, but like I guess the assumption is that it's too late at the pre-training step. Like, is there anything you can do? But like the big question here is like all is lost. Is all lost if like you've messed up the pre-training step, or can you recover at the fine tuning?
I think it's possible, right? Like I guess because I think the methods you're talking about, typically classically, they don't study transfer learning, right? It's just you have already just like a bias data set already trying to fix that. So you could probably imagine maybe the network itself, it's just a representation of a bias data set and then you're trying to fix it. So all of these biases that I talked to you about, I sort of gave them to you. I knew what they were ahead of time, and we could test whether the bias transfers. But you probably also want to know if you're actually downloading these pre-trained models from OpenAI and Google, how do you actually find the biases in them in the first place? And which bias should you even be looking at? Because as some people mentioned earlier, not all biases are good. Some of them are bad, but also some of them are reasonably expected. Right? And so we want to know what are the biases we should be looking at, and how do we actually find them in the first place? Now, we can't really do this for OpenAI and Google because they didn't really release any of their data. So it's a little harder for us to do this. But if you do have access to the data, one way in which you can understand the bias of transfer learning is to look at your pre-training data. Okay. So the way we're going to look at our pre-training data is using this framework of influence functions. And in the simplest form, an influence function is just asking the question, what happens to your test performance when you've removed the data point? Okay. And then what the influence function tells you is the influence of that data point is sort of how much it affected your test performance. So here this is a real practical example. So we have our data set here, and here we have a data set where we've removed one single example here. Then the influence, roughly speaking, this is not a very rigorous treatment of influence functions. I apologize if you know what they are. But the influence here is just the accuracy of a model trained on this guy minus the accuracy of a model trained on this guy. So that's the influence of a single example. Now, if you try to do these influences on these deep networks, you probably will run into several problems. Two of which are just that when you try to estimate this value, because we're training neural networks, there's a lot of noise. And so when you train this guy and then you train this guy, there's a lot of noise, the accuracy vary, and then this actual difference is then also going to vary. And then also because we're only removing one data point, these differences are really small. Like maybe this is like 95.1 and this is like 95.09. Okay. it's very, very small differences. So because there's a lot of noise and a lot of different and very small differences, it's actually very hard to compute these for deep networks. So the main tool that we're going to use here is something called data models, where instead of removing one example from your data sets, we're actually going to remove a subset. Okay, so we're only going to train on a subset of our data. And so then let's say in this case, so the black corresponds here to data that we removed. So then we're going to train a model on the subsets, and then we get some accuracy. And we're also going to create this one hot encoding vector here, which sort of indicates what data is present in the subsets that we train on. So you can think of this now as like this is our data set, this is now our training data, right? And now we just want to fit a model to predict the accuracy on your subsets given what subset you picked. And this mapping that we learn is what is called the data model. And so just like very briefly at a high level how this procedure works is first you just sample a subsets of your data set, then you train a neural network on every single one of these data sets. And then at the end of the day, then you fit, in this case, we're going to use a linear model to predict the accuracy of the subset from the subset one hot encoding. And then the linear weights that we get out of this linear model are the influences.
Are the subsets sampled uniformly at random or in some way?
They're subset uniformly at random. So nothing clever. So then you can think the linear weights are now the influences. So a positive weight means that a single example has had a positive increase on the accuracy over many subsets. Whereas a negative weight is a negative impact on the accuracy, again, over many subsets. And so now the idea that we're going to do here is we're going to take this framework of data models and use this to now understand transfer learning. Okay. So it looks very similar. We're going to take, again, for now it's our pre-training data. We're going to look at subsets of our pre-training data. We're going to now pre-train and fine-tune to get your transfer accuracy, and then fit a data model for a linear model here, predict your transfer accuracy from the data that you've included in your pre-training.
How good are these G's? Like, I guess what I'm wondering is, I guess depending on how large the subset you choose of data, it seems like you might have very, very small probabilities of ever seeing any data point once at all, or any data point more than once.
Yeah, it depends on the subset size, but usually you can pick anything between 80 to 30%.
Okay, so most data
points get seen many times.
Still in there.
Like the thing that's confusing me, and I'm sure the answer is just that like it works and I'm wrong, but like the thing that's confusing me is that I would think that like if you're sampling a large fraction of data set uniformly at random, the accuracy of the model you get sort of concentrates around its mean over the expectation of the sampling, and that basically all of the labels in this data set, what is the accuracy of FS would be like basically the same thing. And there's sort of not much signal to predict.
That's kind of what I'm.
But I guess you're going to tell me that that's not true.
Yeah, so if you, I guess when you make your subset closer and closer to a full data set, then yes, then the transfer here, your accuracy that you get out of it is also going to converge closer to just that single performance value. So yeah, usually you would need to take a subset that is small enough that you actually get variation.
But like 80% is small enough.
For certain data sets.
Okay.
It depends on the data, right? Some of them need a lot more data.
Maybe not for like some of these open, like these 500.
Yeah, maybe not for the 500. Okay. Do you have a question?
Well, I'm just wondering, like, if you train on the multiple models on the full data set, how does the variance across the performance correlate with what you find if you just train on subsets and the numbers? That makes sense. Like it's related to this.
Yeah, so the variance, if you just train on the full data set, that's sort of like the inherent training.
Yeah,
variance,
correct.
right? So, when you train on subsets, you will still have that inherent training variance, but you'll have more variance from the fact that you're only looking at a subset of it.
So that is in fact the case, like that is something that you can measure. Okay.
So you're focusing on the individual, but there's possibly correlation as well, right? I mean, I guess you're not counting that. Two data points together affect accuracy a lot more than.
Yeah, so the correlation between multiple data points is not explicitly being modeled together here because we're using a linear model. They do actually show up to some degree because we're dropping subsets. So there's a random chance that two data points get dropped at the same time, in which case that effect does get measured, but it's not being modeled explicitly. Yeah.
So I guess one more question. What's the motivation for using accuracy as a notion of sensitivity for data point as opposed to like my model's predictions changing if I remove a data point?
Yeah, so that's a good question. Why am I using accuracy here? You don't have to use accuracy. You can use accuracy on a single data point.
Okay.
So actually, this whole thing you can run for each test example in paragraphs.
But it still seems like you're censoring information here, because I might imagine I could remove a data point and that might change my predictions on a lot of test points a month without changing their labels, the predicted labels, right? Like maybe my probability of cat on a cat image goes from like.
Why is this accuracy like 0.1?
Yeah.
So you can actually do this on the budgets.
Okay, that's the next one.
I just put accuracy.
Sure, okay.
Okay, yeah, so that's sort of the framework. We're gonna use this framework here, right, to understand which pre-training data points had high influence and which ones had small influence. The whole data models thing is really just a way to calculate these things with lower variance and get an actual good estimate of what's going on. And now we're gonna, we're just gonna run this on transfer learning and see what happens. What does it pick up? So the first thing that it picks up is harmful training data, right? So if you look at the negative influential data points, right? Negative means that it reduced your accuracy, and so these are harmful to some degree, right? And so if you look at the most negative influential data points in your pre-training data, you'll find that there's actually quite a few data points that are significantly negative influencers. So in this case, here where we have here we're transferring from ImageNet to CFAR10, and we're just looking at, for example, here this is the dog class, and these are the most negative influencers from ImageNet for the dog class. So these classes here, so there's like sorrel horse, lesser panda, barracuda, including these images from ImageNet, reduces your performance on CFAR10 dog after transfer. As for why exactly? Now, I can't give you a very systematic answer as to why, but if at least in the case of sorrel horse, you look at an actual sorrel horse, they look like this brownish, whitish horse here. And then if you look at CFAR10 examples that this has a very big negative influence on, they look kind of like this. So if you squint at this and you look at this dog also has sort of brown and white, and it's also standing in almost the same kind of position as the horse. So you might believe that that's maybe why this sorrel horse is a negative influencer, because it's confounding now this dog with the horse. And you can do this sort of experiment where you take the negative influential data points, so all of these things here that negatively influence our accuracy, and remove them from your pre-training data, rerun the whole transfer learning pipeline, and you can actually improve your transfer performance. So one second. So if you do that, you get something like this. So here the gray flat line here is sort of your baseline accuracy when you have just your standard full ImageNet training. And then this, full ImageNet training and then transferring to CFAR10. And then this blue line is if you remove the negative influencers from ImageNet, did your pre-training, and then transferred to CFAR10. And the x-axis here is just the number of classes from ImageNet that you're removing. So if you're removing negative influencers, so negative ImageNet classes, and you're removing the negative ones, your accuracy actually, your transfer accuracy actually improves. On the flip side, if you remove the positive ones, your transfer accuracy. Okay. Yes.
So I assume this, when you were pre-training on ImageNet, you're doing supervised learning.
Yes, this is all supervised.
So do you have any results on like unsupervised pre-training?
No, we have not done unsupervised. So I mean, it'd be interesting to see how you can do this on unsupervised. So the reason, the nice thing about image, like a supervised pre-training, is that you can calculate influences of entire classes and remove them sort of all in aggregate. If you have an unsupervised data set, it's sort of unclear what are the subsets you got.
I guess part of what I'm wondering is whether the bias is because it is the training and target, of course, like.
It's possible.
And if you did unsupervised.
That's totally possible. I don't have an answer because I don't know what the answer is. It's possible. Yeah.
I guess I'm curious about the data difference here, like learning with living. You could just iterate from class to class through the pre-K. 1,000. Right, is learning this learning on the left less than 1,000 subsets needed from where does it fall?
Yeah, so the subsets at the end of the day are to make it more to amplify the effects. Right? So if you only remove one ImageNet class, then the resulting effect that you see after transfer is actually not that much. So that's sort of the noise in training starts to drown out the difference that you see.
So this graph seems to be the opposite, but where I can remove a couple of I really just need to get up to like.
Well, so I guess in this graph right here, the yellow line here is if you remove at random, right? And so if you remove a bunch of like I guess up to 200 classes at random, your performance doesn't change. Right? And I think that's like maybe around 600 you see a small change. So that's why we have to remove more than one.
How many data points do you have?
So in this example, it's we're removing the entire class. All right, so we're running out of time, so I'll just give you a quick overview of some of the other things you can find out when you start looking at what's positive and what's a negative influencer. So if you look at things that are positive influencers, so things that really improve your accuracy on specific data points, it turns out that a lot of things that really improve your accuracy are copies of your test data. So very positive influencers are data leakage. Okay? In this case, it's so CPAR10 is just the 32 by 32 resolution version of the thing that was highly influential in ImageNet. You can see this thing, there's a bunch of examples here. And then on the other hand, if you look at the very negatively influenced examples, you start to get sort of very confusing data. Right? So things that hurt your performance are things that are very confusing. For example, there's a lawnmower in the sky. And this hurts your ability to predict airplanes because you don't normally see lawnmowers in the sky. And then I guess the last thing that I'll just highlight here is that if you use these influences, you can actually use them to identify subpopulations in your target data set. And so in this case, in this example, let's look at CFAR10 birds. CFAR10 birds does not have an ostrich class, but ImageNet does. So what we can do is we can look in CFAR10 for data points that have high influence from ImageNet ostriches, right? And so anything that's highly influenced by ImageNet ostriches are more likely to be an ostrich, and then you can do that and automatically pull out all the ostriches in CFAR10. Right? So just a few quick takeaways here. It's just at the very beginning, we talked about biases that transfer to different tasks. And these biases can help you, but they can also hurt you. And at the end of the day, if you want to find out what these biases are and like how they're actually, how is this transfer learning pipeline actually working, you could potentially use things like data models or other influence functions to see how your pre-training data is affecting your downstream performance. And this work is, I guess, this is all sort of based on the two works here on the slide. And I will end it there, if there's any questions.